¿qué tal? Me llamo Toby, and this is all my Spanish. That's about it. So it's so nice to see you all here. I was told, though, that you're all sitting here because of the next speaker. So I was told that he's so famous and that everybody was just sitting here to get a seat for the next talk. And I got told that multiple times, right? And it was quite him, actually. Well, thanks again for you for coming. So let me take a picture of you. It's so amazing. Make a loud, round of applause. Woo! I love you guys. You're awesome. You're awesome. All right. So, as I said, I'm Toby, and we'll be talking about virtualized USB fuzzing today. So, the title is a bit more complex than that, but I'll try to reduce it down to the important bits. So, this is roughly the agenda. I will first talk about USB, what it is, what it does, why we live with USB, and why it's actually an interesting target. Because you might ask the question, the valid question, why would you ever bother looking into USB security? And I will try to answer that. And after that, we'll hopefully try to get to the more interesting parts, the attacking parts, how to actually do or how to actually carry out USB attacks. And then I will show you some of the things that I found out that I discovered during it. So this is me. You are very, very welcome to write me an email if anything is unclear. I publicly announce my public key, the fingerprint of my public key. So if you want to sign that, you're more than welcome to do that. If you have any question, I ask you to ask that immediately. So show up, make yourself heard, and do anything that makes me see you. If I ignore you, or if I don't see you, then it might be either the case that I don't like you, or that I just don't see you. So in that case, you could come up with a beer on stage and make yourself known, and we'll get that sorted. And I will try to make that not just a plain talk, but also show something off during the talk. And I hope we will do that in time. I was told we're quite tight on time today because apparently the place ran out later on. So I'll try to get everything done in my time. So USB. Why would you ever bother looking into USB? So it turns out that every major operating system out there has USB support. So even Mac OS, right? But not Hurt. The GNU Hurt does not have USB, but we don't care much about that. So if you have any PC running, any reasonable PC that is reasonably in use, it will have USB support. USB claims, like the USB consortium, claims that USB is the most successful technology ever sold. So by now, I think they claim to have sold 8 billion units or so, selling 2 billion a year, and that makes it quite a successful technology, they say. And I mean, it's true. Every tiny device has USB support, right? And even our phones do everything nowadays via USB. And I will come back to those phones later on. However, USB, despite the fact that USB is so widely deployed, we cannot easily assess its security right now. How would you, say, inject fake messages into the kernel? You cannot easily do that. It's not that I'm aware of. So if you wanted to implement arbitrary USB behavior, you would probably have to buy a development board and program its microcontroller or get some firmware onto that. And it's all a bit complicated, I guess, I'd say. And I forgot about that point. So the USB drivers nowadays mostly rely on kernel space. So it's a very powerful target to attack. Although this is shifting, right? I mean, especially for webcams and all that, more and more drivers are getting into user space, at least on Linux. But as we are talking today, there are at least 400 USB drivers in the Linux kernel, just for USB devices. And that is poses a large attack surface, right? So it's a very, very powerful target to attack. What else? What are practical applications of USB? One is this. So what you see is first of all, a piece of paper and a pen. And it's not an ordinary piece of paper, and it's not an ordinary pen. The paper is a ballot for an election back in Hamburg, where I come from, Hamburg, Germany. And the pen would work together with the paper to find out where it has been used, on which spot the cross was made. So they tried to introduce that voting machine, I call it a voting machine, and they failed fortunately. But whatsoever, that technology, the pen technology, uses USB to transfer its data. And imagine yourself being the next mayor or chancellor or president of whatever country just by hacking the USB. It's amazing. So another, probably more scary target would have to be. So that's an inside entertainment system, and we see the USB port very well exposed. The system, I was told that they run either Linux or VxWorks. I've seen one constantly booting all the time, so it was probably locked up or crashed all the time. It was not me though, so that's broken by itself. And yeah, I mean, imagine yourself crashing an airplane just with a USB port, right? So it's a very, very dangerous. It might be a very, very dangerous technology after all. Just because it fits so nicely with the bomb and the USB, I have prepared a laptop. We tried to hook it up with the projector, but unfortunately it didn't work. So what you see here is just an ordinary Linux. I just booted like a Linux system. It's nothing fancy, and it just dropped to the shell because it was quicker. Right? I could have booted like the fancy X system and all that, but I just didn't because it was quicker. So on the other side, I have my phone, a Nokia N900, which is a very good phone. It runs a real Linux system, and it is able to be a USB client. And what I will do is I will hook up the phone with a laptop, and then the laptop, the kernel, eventually will crash. I'm sorry for you, but you probably cannot see that very well, but I tried to show the first row, and you kind of have to believe that it crashes. Right? And remember the beer I will give you, folks. So now with all my nervousness, I have to make it work. And I'm not doing anything like fancy on my phone. I've just loaded the kernel module that made it act like a client, and now you might see that it just boosts and like it's not working anymore. It just crashed. That's because of Nepal. Now come on, guys. So beware of my phone. So try to not expose your laptop close to the phone. So yeah, it is, and it is quite simple, right? It's just like plugging it in and just wait a second and then boom, off it goes. So what is USB anyway? Just a short introduction to that. Back in the day, when I was young, and I had a joystick and I wanted to connect that to my computer, it was a pain in the ass. It took a day or two, because you would have to figure out the correct interrupts and all that. And it was like a major thing, a major project to connect like any peripheral devices to your computer. So the vendors got together and thought about, well, what would be the craziest thing you could imagine for peripheral devices on a computer? And they came up with all these things, with all these features that made me wet myself because it was so amazing. So USB would be able to configure itself. So you would plug a device in via USB and it would just work like that, without like configuring any interrupts or I/O ports or whatsoever. And just amazing. And you could hot plug it. Yeah, that means you could plug it off the computer and plug it in while it's booted. Imagine that back in the 90s. It's like amazing. So they did that. And eventually it worked out. And as I told you, they claim it's the most successful technology. So yeah, USB was trying to replace the technologies that were used back in the day to do, say, small data transfers. So to hook up your laptop or your printer or your scanner, to replace that and to unify that and to make that work properly. And well, the USB protocol itself is not too bad, so I guess they succeeded in doing that. However, USB is not all nice. It's pretty good, I'd say, and the standard is not too ugly, so I invite you to read that standard if you have ever time to. It's like 700 pages or so, the base standard, and then plus like whatever, thousands of pages for the additional standards. Don't bother with that. Yeah, it's a nice enough standard. It's not all good though. So the most annoying point probably would be that the devices cannot talk to each other. So USB is like a host-initiated communication. So your PC that runs the USB, that runs the USB stack, would always ask every device whether it has any new data, and the devices could not talk to each other. So if you wanted to copy data from one hard disk which is attached via USB to some other hard disk which is attached via USB, then these devices cannot talk to each other directly, but rather all the data has to go through the host, which is kind of annoying, but initially that wasn't necessarily their use case, plus USB, it made USB much cheaper to build and to implement. So apparently the USB technology is very cheap compared to other competing standards like FireWire. You just need a fraction of the transistors to build a USB controller than you need to build a FireWire controller. So this is why we have all those devices implementing USB, because it's rather cheap. The polling mechanism, that's what I was referring to, is a bit stupid as well, right? If you think about it. You have all these keyboards and mice connected to your computer, and the host has to ask every couple of milliseconds, do you have any data? Have you pressed the key? Do you have any data? And it's just too stupid, right? But coming from where we were back in the 90s, it made kind of sense. So USB 3 will eventually fix a few things, but we'll come to that later. All you need to know for now, and for this talk, is that USB is all about packets. So, and this sounds familiar, right? It's almost like in an network where we send packets back and forth. And there's different types of packets. First of all, there's the setup packets, which are used to, say, configure the device and make the auto configuration work. And then there's packets for sending sending data to the device and getting data from the device to the host. So there's more detail of the USB, of course. I cannot explain USB in 10 minutes, of course. But this is the most important bits that we need for now. And this is roughly what it looks like, right? So at the very bottom, we have what I term the electrical layer. Basically the USB controller, the hardware, the chip that deals with all the electrical stuff, getting the pin up to 5 volts and sending some current over there and all that. And on top of that, you have your operating system, the kernel, and the actual USB stack driver would talk to the USB chip and make sending of packets happen, put them into chunks and send them off to the hardware and all that. And on top of that are the actual device drivers that take care of talking some kind of protocol to the device. So imagine you have a webcam. You would then have a webcam driver over here. Imagine you have a hard disk. You would have first a USB hard disk driver over here, but it would then be smart enough to reuse existing functionality from other drivers. So it would go off and take bits from the SCSI subsystem to not have to implement that itself, which is very smart. And then on top of that, we have the applications making use of the device. So you imagine yourself in iPod managing applications. So it would eventually talk to the device via USB, but it's not a driver or anything, so it's the application using the device. And for us, all of that, but the electrical layer is under attack. So what we are examining, or what we can examine, is the security of all that. So beginning from the stack, going through the USB drivers, and with that, the other drivers in the kernel that are being reused for the purposes of using that over USB, and then of course the applications on top. And how does the USB stack know which driver to load? How does the operating system know which driver to load from the disk and prepare and everything? This is done via the so-called descriptors. USB uses so-called descriptors a lot. And these descriptors are organized in kind of a hierarchy like that. So each device would have a single device descriptor. And that would tell the operating system, well, I'm device such and such, my name is this and that, I was produced by whoever. And after that come the different configurations that the device has. You could imagine yourself a hard disk, which would be able to be in sleep mode and in normal mode. And one configuration could be potentially that the device would be in sleep mode and then offer less services than as it would if it was in full operational mode. So these are the different configurations. It's basically, you basically tell the device to offer different services with different configurations, and the device can then act on it. The interfaces, finally, they can define the protocol to speak. So if you have a DVD drive via USB, you could think about an interface reading the data from the DVD disk, or you can think about an interface playing the movie. Because it's like you could imagine yourself at different ways to talk to the DVD drive when you want to do different things. And finally, the endpoints are they describe the pipe that you use to build to transmit data in and out. So there's a lot of descriptors, and they contain a lot of structured data, and it turns out that some, say, operating system builders already failed to do that problem. And what does that look like? This is a device descriptor, and you don't necessarily have to see all the numbers and all that, but you see it's not too much data, and it's structured data, so we have here fields indicating the size of a packet, and we have indices to some string arrays and all that. And that's very easy target to attack for now. And if we were able to control these descriptors, if we were able to send any arbitrary descriptor to the host, then we could make the operating system load any arbitrary driver, and we could assess its security. And it turns out we can, which is good. So what happened with USB and all that? So you might remember a couple of months ago, I think it was like 1.5 years ago, 1 year ago, I think. Yeah, pretty much 1 year ago. A PlayStation 3 hack was going around, and what it essentially did was it was announcing some length of the whole descriptor tree that I was referring to a couple of slides ago, and it then changed the size. So the USB stack cannot necessarily know upfront how big all these descriptors are, right? Because you don't necessarily know how many configurations a device has. So the solution to that problem within USB is to just read a couple of bytes, and within these couple of bytes, there's a length field. And that length field would then be used by the operating system to read the full thing. And what the hack was doing was that it was changing that size. So in the first read, it would announce whatever length, and in the second read, it would announce a different length. And the operating system of the PlayStation 3 was failing to do that problem, to handle that problem. And it turns out, it's not only that, like, PlayStation's only operating system, you could argue, well, these are not necessarily operating system makers, they don't have any clue. It also happened to fail with Solaris just recently. So Andy Davis presented on Black Hat a presentation, or well, just after Black Hat, I think, he showed, or he wrote an email saying that Solaris is actually prone to kind of the same vulnerability. And well, there are many more issues that are related to USB, but not necessarily directly. So there are many partition table parsing issues which do not necessarily have to do anything with USB. But of course, if you have a USB pen drive, a USB mass storage device, you could make the operating system parse that partition table and it would crash. But I haven't listed them, but you can look that up. It's not hard. So, what happened now? Alright. You could say, well, USB security is not necessarily interesting because you would need to have physical access. And often people say, well, physical access, if you have physical access, then you're doomed anyway. And your operating system is not about to protect you against physical access. And, well, I say, no, that's not necessarily the case. Because we have technologies like full disk encryption, which actually prevent your artist from being grabbed and stolen, like when somebody has physical access. We have technologies like password-protected screensavers that try to prevent anybody from accessing your desktop when anybody's around. So I say the operating system, to some extent, tries to prevent people from doing anything malicious with the machine when they have physical access. And whatsoever, there are technologies that make you not necessarily need to have physical access to the machine. So it turns out that there's a technology called USB IP, which does USB, which speaks USB via IP. And it's readily available in the Linux kernel. It's not turned on by default, but it's readily there. You could use it today if you wanted to. There's also something called wireless USB, which hasn't really took off yet. I don't know, I think they have still problems with license issues. So what they do is they use a radio to communicate with the device uses radio to communicate with the host, and they use very high frequencies, and I don't think they have the necessary license to get that up and running in every country yet. So this, at least not in Germany, it's not popular at all, the wireless USB. So the point being, it's still interesting because you don't necessarily need to have physical access to the machine. So a quick introduction to the fuzzing, because the title is about USB fuzzing, right? So back in the day, it was quite popular. Everything was being fuzzed, and everybody made a fuzz about fuzzing. So, and there's one guy claiming that he coined the term fuzzing. It was some lecturer at some college in the USA, and he was throwing random data at the standard Unix tools back in the day. And it turned out that many of them crashed when you just threw any random data up to the program. And yeah, so it got a rather big revival, I'd say, a couple of years ago. Just after fingerprinting was hot, and then came fuzzing, and after that, I don't know, there's waves in computer security, you know, sometimes this technology is hyped and then it's not. Back in the day it was fuzzing, so everything was being fuzzed. We try to get smart, or to do fuzzing in a smart way. So we do not necessarily want to try to make something crash by just throwing random data at it, but rather modify existing data structures to penetrate deeper into the code that's being assessed. So imagine your code expects some structured data, and there's a checksum field. Your code would very quickly bail out on the input if the checksum wasn't right, or a length field. By throwing random data, you have a hard time getting these fields right? Because you would, it takes you a long time until you have the right checksum in order to progress deeper into the code that's being assessed. So what we try to do is we try to be smart about it. We try to have knowledge about the data that the program expects, and we then try to modify the data in that structure and try to adapt the fields necessary to penetrate deeper into the code. So while that sounds nice, Microsoft thought so as well, and they filed a patent back in 2008 claiming that they invented fuzzing, smart fuzzing. So it's still an application, but and it's not been decided yet. But if you do anything with fuzzing, you might look into the patent and see whether they got it granted or not. It's just meant to be a side kick against software patents. So if you want, you better fight against software patents, because otherwise you cannot do the fuzzing anymore. So go to your government and fight against software patents. It's a big issue. And how do we do the fuzzing? Well, me being lazy, I just reused Skatey. So Skatey is a Python library, a toolkit for doing all sorts of stuff with network packets mainly. So it's been designed for sniffing, manipulating, crafting, and sending off network packets, Ethernet packets. And we just reuse that functionality because USB turns out to be quite similar, right? We have packets as well, and we have structured data in that packet, and we could just reuse Skatey to do all that what it does with network packets, but with USB. And we get all the nice features from Scapy for free with that, including the plugin, which is nice. And also, it's written in Python. And I was told that Argentina is a big Python, or like there's many Python people in Argentina. So if you have free time and want to like have some project, have a fun project to hack on, have a look at Scapy. It's like really good. And it's got interesting technologies as well. They use their own test suite with a web interface and all that. So you might very well have a look at that and contribute to that. So, and Python, if it's using Python, it makes it rather easy to adapt it to the USB models. And it makes it very easy to reuse it later on in the old fuzzing process. So, talking about the smart fuzzing, about modifying, or talking about knowing the structure of the data that the program expects. We might want to get that real data first. So we might want to obtain valid USB communication, and then having that data, we might want to modify bits and pieces in that modification data, in that communicated data. So how would we do that? Currently, we can load a module for the Linux kernel that would print all the data flowing on the USB. But it's much of a hassle actually. So it's like very verbose. There's loads of timing information, and it's very crowded, and you would have to parse all that yourself. It's not necessarily nice. And you could of course read the specs and implement like the valid data yourself, but that's of course a hassle. So what we did was making QEMU type out the actual data that is flowing on the USB. And it would type that out and read that back in. So it's kind of a filter functionality. And it looks like that. So we have the host system, your regular Linux or Windows desktop PC. You would run the virtual machine using QEMU. And QEMU would talk to a filter, or would send its data through the filter before the data gets to the USB device. And the same story on the way back. And that filter could, of course, write the data that it's seeing. It could write that out to the disk. It's not too complicated. So, and this is, as I said, this was done. And I want to show you how that works. So, I'm preparing that over here in my other terminal, and I think I need to make that go there. No, hang on a second. Like that. All right, there we go. So we start QEMU first. There we are, and then we tell it to set up the filter, and now it expects something on the other end of the pipe, so it will block until we until there's something on the other end of the pipe. We start the filter program. Now it actually, the filter is set up now, and now we want to actually have some USB communication. So I plug in my pen drive. So I just attached the pen drive. Mouse. Weird. That's strange. Cannot like press anything, it doesn't react. Alright. Alright, I'll try that one more time. We tell it to set up the filter. I'm confused, but I recorded that on video as well, so, because I knew it could fail, right, for whatever reason. So I recorded that on video as well. But the filter thing itself is not too interesting in itself, so I will not show the video. But we can watch the video later if we have time. So what it did, or what it was supposed to do, anyway, and I've done that 1,000 times beforehand, right? So I've got loads of these dump files on my machine. It just, for whatever reason, just didn't work just right now. So it would write out the communication that is going on the bus. It would write that out onto a file. And we could use that file to do whatever we wanted with that data. So one thing we could do is we could replay the data to the screen to see what was actually going on. And let's take this one. So we see all the data flowing on the USB. It probably doesn't tell you much at this stage, right? But if you want to see what's going on the bus, it's very helpful to see what packets are being sent off and back. We can also, with the filter, of course, modify the data on transmitter, right? So imagine you have a program sitting between your virtual machine and the actual USB device. The program could very well just change the data on the fly and introduce random bytes. And there's an interesting experiment which I want to show you. Let's hope it works. We will do exactly that. We will change the data in transit, and we will do that with a mass storage device, which I will plug in now. It's a bit tiny, so I have to fit it. There we are. So, set the filter up. We do come on. So set the filter up. Then we add the mass storage, and where's the machine? There it is. Oh, Jesus Christ. Alright. So, I wasn't expecting that to fail that hard. The video. And so let me just move the window. video I recorded, knowing that it eventually would fail on a live demo, right? So, I recorded that a couple of days ago, and what I was doing is I plugged my pen drive in, and beforehand I created a file which is only A's in it, only like loads of capital A's. And first, the virtual machine will see the USB pen drive without any filter in the middle, so it will see the all A's, and then eventually the filter will kick in, and the machine will see something different. We'll see all B's in that way. So this is the pen drive on my host system. So not in the virtual machine, but on the host itself. It's only A's, as you can see. Okay. So the machine is started. And now I search for the pen drive, get the USB ID, and it's being attached to the virtual machine. So there it sees the pen drive being attached. First we mount that to some location, doesn't really matter. And now it reads the file, and it's all A's, as expected. And now the filter will be set up. And the filter will replace all the A's with B's in this case. Well, not just yet. So we drop caches because the operating system would have cached the file already because it's smarter than it's a smart operating system, right? So there we go. This is like all B's. So, and this was an interesting experiment because I know people building kind of USB water gates. So before entering a building, say a security relevant building, you would have to plug your USB pen drive into some machine that would assess your USB pen drive, like converting all the documents from Word to plain text or whatever, and would scan for viruses and all that. And well, and if you haven't done that, you couldn't enter the building, right? So the experiment would tell that you could very well build something that would present data on the first read and present different data on the second read. So you could very well just bypass that Watergate application thing by building such things. So let's get back on track. So what's the QM thing I was talking about? Just a quick introduction to that. It's a virtual machine, and it's written by that really ingenious guy, Fabrice Bellard, and it's a really good piece of software actually. And it does full virtualization, unlike Zen or OpenVZ or whatnot technology exists. It's like basically like VMware, but free software. And it already has virtual USB devices, not like virtual box as of a year ago. So that made it actually, well, it made it rather easy to implement that functionality. And well, I say that now, but when I was doing it, it was not necessarily that easy, right? So what we could also do, we could take that filter functionality to do the fuzzing array, right? We could like modify the data in transit, and just inject random bytes into that. We could very well do that. But this is, of course, not necessarily convenient because you would still have to plug the device in physically. You would still have to sit in front of the machine, plug your pen drive or whatever in, and then start the filter and all that. And we don't want that, of course. We don't want to physically plug something in and then plug it out and plug it in again. Because that's, I mean, you cannot go out and drink beer while doing that, right? You want to do that, to have that done automatically. So ideally, you would run some program. It would take a whole night. You could go out and come back and see like all the crashes on the operating system. And in order to achieve that, we have built virtual USB devices. That is, the virtual machine, QEMU in this case, would not talk directly to the physical USB port on your PC, but rather to a program that is running on your host via pipes. So you would not need to physically plug a device in and out and in and out again, but rather start a USB device program that would act like a USB device and send the packets to appear as a USB device. And that means that you can implement arbitrary USB behavior in software. And you do not have to program a microcontroller on a development board, like I was saying earlier. So, yeah, how to do that? It's, well, now I'm saying that, it's not too complicated. So, as I said, there's support for similar functionality already within QEMU. And what you would do in order to achieve the virtual USB device functionality is take some simple driver, like the mass storage device or a serial device from QEMU, and basically extract make it extract the packets to pipes, make it send the packets to pipes and read it from a pipe back. And your USB device is then implemented as a process running on the host. And it could be as simple as cat and echo. Right? You could take existing dumps, existing communication like we've seen earlier. You could take that and just cut it into the pipe, and it will work. Well, we could try to demo that, but I'm a bit afraid now. So, but I've done that like dozens of times, and it should just work. So you could use cat and echo, and it will work. But then, I mean, it's just simple, right? What you want to is something more sophisticated, and this is where Scapy comes into play. So Scapy has a very, very good functionality for being, say, stateful. They have an automaton which, like, can hold a state and react on special events and all that. So you could implement your USB mass storage device using Scapy, and then, while using that, do some fuzzing in between. And it would kind of look like that. So you have the host operating system. It runs the virtual machine using QEMU. And instead of QEMU talking to the real device, like we have seen in the earlier picture, it would now talk to some other process on the host via pipes. Oh, Jesus Christ. Sorry about that. So, let's try it one more time. It should work, as I said. So we start the machine, and what we will be doing is we will start a virtual USB device. That is, we will start a program that reacts like a USB device, and the guest Linux system will show that there is a new USB device. Although I'm not plugging anything in, right? It's just the program. The process that I'm starting to use that, which acts as a USB device. So, first the machine again. There we go. So, I've told QEMU now to USB add and emulate a device from that pipe address, from that pipe file. And we now start the program that acts as a USB device. Where's my mouse? there you see the packet going back and forth. And as you've seen, I haven't attached anything, right? It's just the process. Oh, it doesn't work. Why not? All right, but fortunately, there's a video for that too. Yeah, sorry that it doesn't work with the live demo. I have to investigate it. So yeah, we'll see basically what I just tried to execute. It will start the virtual machine. It will tell the virtual machine to attach the USB device, and the process at the other end of the pipe will just like behave like a USB device. So the virtual machine is started. We tell it to attach the USB device. And you see all the descriptors, by the way, right? That I was talking about earlier. And there's the device. So, yeah, it's actually very embarrassing that the demos don't work, but as I said, or as you've seen, I recorded that, so it kind of worked. So, what else can we do? Besides all these virtual USB device functionality and all that, QEMU has an API interface via JSON, so web technology, and I basically brought that to Python so we could control QEMU from Python. And what this reads is a tiny program using that Python API to attach as many USB devices as possible in order to test the host operating, the guest operating system for like its function, for its ability to cope with many USB devices. Unfortunately, this program will make QEMU crash and not the guest operating system. So there's a bug in QEMU that prevents like this test from running successfully. And what we can also do is find out where we are actually attached to. So we've seen the crash on the Linux system, right? And what we can also do is find out whether we are attached to a Linux system or, say, Windows or a Mac or whatever. And then, once we know that, run a targeted attack. And that's very powerful if you think about it. So you can basically attack any system with your tiny phone. So how can we find out? It turns out that the operating systems behave differently on the USB. I mean, it's actually not that surprising, right? They were implemented differently, so they have different like ways of working. And it's actually very easy to find that out, how they work differently. So this is the data that you would need in order to find out whether you're attached to, say, a Linux or a Windows system. So we did the demo on the laptop already. So what's left to be done? There's actually loads of stuff to be done. So one thing that I think is very, or would be very interesting, is to get these virtual USB devices that are written in Python, to get them onto those phones. Because so far, you would have to write a kernel module and load that kernel module in order to speak to a host via USB and make it crash. So if you could easily, I don't know, say copy the Python script onto the phone, that would be really awesome. Well, there's USB 3 coming, and it's not too different from USB. Well, you could argue, you know, you're talking about USB 2, it's so 90s, it's not important anymore. But USB 3 is not too different. Its main features are speed. It's like very fast and to compete with FireWire. And it can also make the devices tell the host that there's data available. So these are small additions to the existing USB standard, so it still is relevant. And what I think is also an interesting project to work on are using firewalls to stress test actually the USB clients. So to find out whether it's a malicious device, whether it's my Nokia hacking phone or it's a regular pen drive. So there's a lot of stuff to be done, and I invite you to hack on it. Yeah, that's pretty much about it. I thank you very much for your attention and for your attendance.
Si quieren hacer preguntas, pueden hacerlas en inglés o en español. Toby se va a poner el headset. Tenemos tiempo para 3 preguntas.
So I take all questions, Spanish, English,
Luego. Hi, right demo. I have a question. I see that you can inject change data in the computer in the kernel mode, but you can also execute commands, for example, for execution program or in the kernel mode access to make and exploit for example, down the antivirus and the host machine to make a reverse command in this system.
So let me repeat the question I understood and say whether this was the question or not. Is the question whether it would be possible to write an exploit that shuts down antivirus?
Yeah. Or execute command in the host.
That would certainly be possible. Unfortunately, we're not there just yet. So, as I said, there's loads of work to be done. The crash on the Linux, it's just a crash. It would be much more powerful if you could actually run commands or like kill processes or whatnot. But so far, it's just a crash. So, me not having any kernel exploitation experience, I cannot. Well, so far, I cannot like go any further with this. So I have to go on that. Yeah, it would certainly be possible, but it's not without technology just yet. So it's like a lot of work to be done in order to get there. Question in the back?
I have a question. Did you find any bugs with it?
You mean whether I found something that crashed the Linux system?
Did you find any exploitable bugs with,
Yeah, as I said, I'm not that much of a kernel exploitation guy, so I don't know whether this is actually any kernel exploitable. But I guess, given that there's like 400 drivers, USB drivers alone in the Linux kernel, and given that pretty much all the subsystems can be pulled with a USB device, I think there's like loads of ground that can be exploited, and especially all those multimedia stuff. So my initial motivation was to fuzz around with webcams and all that, because I have never seen any like complete non-body multimedia decoder. So far all the image decoders and all that have all been broken. So I think that when we tinker around with the webcams, especially webcams, and do funny things like announce too high or too little resolutions, then like my feeling is that everything will crash in an instant. But I haven't looked into that detail yet.
And another question back with the fingerprinting thing that you need. Did you find a way to fingerprint different type of Windows, or just Windows from Linux?
Oh, I haven't. Well, I barely installed Windows, and it's hassle, and I don't like that. And I did that with tears when I installed that. So I just looked into whatever it was, like XP or whatnot. So, but it's very simple. I mean, once you install Windows, you can like fingerprint it easily. One just has to do that.
One last question.
Here in front.
Hi. I didn't understand which are the prerequisites to run this application. I heard you saying that you need to have the USB driver module in back mode, or is it possible to do this attack in any Linux kernel?
So, is the question about running vast disaster technology? If it is, then you just need a C compiler and basically a Linux system and Python interpreter. And yeah, I think that's it.
And when you replace the data within the USB, you only can do that attack in your QEMU console. How do you step in the middle of the communication?
Okay. So QEMU was instructed to type every byte that is sent or received on the USB, to pipe that out to a different program. And, well, then that program can read all the communication and write the filtered communication back. And if it was a simple filter, it could just like write the bytes back without changing them. And if it was a more sophisticated filter, it could change the bytes as they were going by.
So basically use QEMU to replay the attack and for further attacks.
Could you repeat the question, please?
So you use QEMU to record the attack that you are going to do later on a physical machine.
Yeah, well, you could do that, but I would say I use QEMU to record valid USB communication, to see what it looks like, to see the protocol, to see how a valid communication stream looks like, so that I can be able to modify bits and pieces in that data stream. Because initially, I don't necessarily know how the protocol for a mass storage device works, unless I read like the 1,000 pages of the spec, which I am too lazy to do. So instead, I let the operating system talk to the mass storage device and have a look on the communication.
Okay, great. Thanks.
Bueno, muchas gracias, Toby.